All right, so we're talking about multiplying vectors with scalars, okay? Not vectors with vectors. We'll talk about multiplying vectors with vectors a little later on, okay? So what we're looking at is something like this. We've got maybe a scalar multiplied with a vector, okay? We are not going to be talking about a vector multiplied with a vector, okay? Not yet. I mean, we will later on, because as it turns out, there are two ways to multiply vectors. One where you put a dot, and one where you put an X or a cross, okay? And we'll talk about those a little bit later on. For now, we are talking about how to multiply a vector with a scalar. All right. It turns out there are many scenarios where you would multiply a vector with a scalar, okay? Let me just sort of put up one of them, for example. In physics, a classic formula that you learn at the very beginning is this, okay? And that's where the acceleration is equal to the final velocity minus the initial velocity over the time, or the change in velocity, that's what this is, over the change in time. And if you think conceptually about that, it makes sense because the acceleration is how quickly your velocity is changing with respect to time. Okay? I bring this up because this is a classic equation in physics. And in this equation, there is vector subtraction, which we learned about yesterday or in the previous lesson. And this is not what I want to focus on, okay? Because I'm not talking about vector addition and subtraction anymore. I talked about that in the previous video. What I'd like to talk about is what if I have to multiply a scalar with a vector? Well, in this equation, you see that there is a scalar, and the scalar is time right here. Because remember, time is a scalar. It doesn't have any direction. And so, I mean, people say time goes forward, so it does have a direction, but there's no need to state that because it always goes forward. So it's not like you have an option of going, west or east. It's like you're always going forward. So anyway, that's more of a philosophical question. Let's get back to the matter at hand. If I were to manipulate this equation algebraically, I could multiply time over, and I could get delta t, or time, times acceleration equals the final velocity minus the initial velocity. And here, bang, there's a scenario right there where I happen to be multiplying time and acceleration, or multiplying a scalar with a vector. Okay? And now, basically, what we want to do is we want to learn geometrically and mathematically what does that look like. So, geometrically and mathematically, what does it look like? What is it? How do we do it? Okay. So let's say I've got a vector A and I've got a scalar of 2, right? Then what does 2A look like? Sorry, what does AK look like? Sorry, what does KA look like? What does KA look like? Well, K is 2, okay, and A is just this vector here, all right? So basically, what I do in order to do KA, it's actually equal to 2A. And just as you would expect, it's twice A, okay? Well, if A is this, All right. Then twice A would be that. And so this happens to be 2A. And so that's the repercussions. It's that simple. What does multiplying a vector with a scalar look like? Well, if the scalar happens to be 2, you just have a vector that's twice as long, but it's pointed in the same direction. So the moral of the story is that you actually have no change in direction there. Okay? So what we're going to end up doing is, mathematically speaking, let's say I've got a 3 times an acceleration, or 4. Let me actually put some units here. Let's say I've got a time of 3 seconds. And let's say I've got an acceleration of 4 meters per second squared east. Then what does delta TA become? Well, it's 3 seconds times 4 meters per second squared east. Oops. Let me change that to a regular parenthesis. And so, therefore, the result is 12 meters per second, and the direction is maintained. It's an E, or east. Okay? And where does the 12 come from? Well, it's just 4 times 3. And notice the units actually kind of corresponded as well, because a second, oops, I hit the wrong button there. The seconds, because a second and a meters per second squared simplifies to a meter per second. All right. And so that's basically kind of like our scenario here. Let me just do another quick example. What happens if I've got a k of -2 and my vector A looks like this? Then the KA vector would be a new vector, but instead of pointed 2 times down in that direction, it's actually pointed in the exact opposite direction. 1, 2. This is what KA is. And these vectors here are supposed to be parallel, okay? So this is the, I didn't draw it very well this time, but this distance is equal to that and that, but it's actually pointed in the same direction, but exactly opposite, I guess is what I meant to say. Okay. So if the vector, if the scalar happens to be negative, not only will it increase its magnitude, but it'll change it around. Okay. If the scalar happens to be a fraction, for example, then it'll cut it in half or cut it into a third or whatever the fraction happens to be. So let's say I've got another k and I've got the vector A, which let's say it's like this time. Okay, like that maybe. Okay. Then Ka in this case is just half of A, which would be basically this vector, but exactly half. So it would be like a little bit shorter. So this would be Ka, and this over here would be A, because it's half. In this case, K is half. So that's kind of like the idea. It's like if it's 2A, the vector gets twice as long. -2A gets twice as long and then switches direction. Half A, the vector gets half as long but maintains its direction. And then I think based on all of that, you can kind of infer what would happen with various other scalars. Okay. Now, let's take a look at some practice questions. All right, so I just pasted down this question. So I've got a trapezoid over here, and it starts at A, goes to B, then goes to C, then D, and back again. So it's trapezoid A, B, C, D, all right? Now, we've got two of the sides defined as vectors. So this little vector, U, happens to be the vector AB, all right? So we can kind of write that down. U vector is equal to the AB vector, and the V vector is equal to the BC vector. And you remember, you can define vectors by a single letter, or you can define vectors by their endpoints and a little arrow above it type thing there. All right. And so now the question is express the following vectors in terms of U vector and V vector. All right. Let me write this a little bit more clearly. And V vector. So I'm basically trying to express the vector AD, okay, which is essentially this vector here, which maybe I'll write it in green, okay, and basically it's, oh, I actually forgot to give us some information. Turns out that V is half of this. My drawing is not very good there, okay? So basically AD then is equal to 2 of the V vectors, all right? Because the V vector goes like this, but then AD can do that and that. Oh, it actually doesn't look like it at all, but I attempted to make a better drawing. Maybe it's like 2.5 in my case, all right? I pulled this example out, but I didn't draw very nice. So let's say it's 2.5, all right? So let me go back over and say, well, why is that the case? Because the AD vector, if I basically travel 2.5 of the V vectors, let me kind of show you this, all right? If I travel, 1, 1, 2, 2. Oh, it actually even looks like 3 even. Oh my. Almost 3. So the AD vector is equal to about 3 of the V vectors, assuming that these are parallel as well, okay? So that's kind of the idea there, all right? Now, I want to mention something right now. This is like super mega intensely important. Some people might be saying to themselves, well, wait a minute, the V vector is way up here, right? And the AD vector is down there. So they're not the same, right? So you can't say that the AD vector has anywhere even close to the V vector, right? Because they're not located in the same position. They're not in the same spot. They don't have the same starting spot and the same ending spots, right? That's true. But as it turns out, what's the definition of a vector? A vector has a magnitude and a direction. And it has that's it. It actually has nothing else. Does it have a location? No, a vector actually does not have, in its definition, a location. And so if one vector happens to have a magnitude and a direction, then it's, equal to another vector. If the other vector has the same magnitude and the same direction, even if they're in a different location. So I can call that vector A, and that's also vector A, because they are in the same direction and they're the same magnitude but they are in different locations. But wait, location is not a characteristic of a vector, okay? And so basically, you don't run into that thing, so into that issue. All right. And so one of the things that I tell people, or if folks learn when they learn about vectors for the first time, is you can kind of treat vectors as if they can just move around wherever you want, right? See this v vector? There it is. I'm going to write it over here. Whoa, all of a sudden it's over there. But you shouldn't be worried about it because it's still the same thing. Because remember, the location of a vector is not part of its definition. Okay, so that's why we can answer this question. So let's express BD, which is let me get let's see. I've used green, I've used red, I used black. I'm running out of colors. Here I got blue. Let's use blue. Here, BD is this vector. Oh my! There it is. It goes like that. Now, in order to do BD, I basically need to go one V vector, right? And then it looks like I need to, I need to go. This is going to be wild. I need to end up here, but I can only use V and U as my two definitions here. What if I go another V vector? All right. And then another V vector. Interesting. Oh, I've gone too far. But now look, if I actually go in the opposite or minus U direction, then I've basically achieved the same goal as starting at B and ending at D. And so the BD vector is 3V vectors minus a U vector. There we go. All right, let's define the CA vector. I need another color. Let me see if I can get purple or something here. Purple. There we go. The CA vector means I start at C and I end up at A. So how can I do that using the V and the U vector? This one's pretty easy. If I go in the negative V direction and the negative U direction, then I've achieved the same goal. So it's basically a negative V minus a U, and I've basically copied the same thing as doing the CD vector. Okay. So there's my solutions to those guys, right? Let's see here. By the way, these guys, are called what's called linear combinations of the original vector here. Okay, so 3V minus U is a linear combination of the BD vector. Just a fancy word there. All right. A couple of other things I wanted to talk about is some properties of this. By the way, why did this show up? Let me actually, I don't want to jump ahead. This showed up here because what we're doing is we're taking scalars in these cases and we're multiplying them by vectors in order to increase the length of a vector in order to achieve another goal. That's why the textbook is asking these questions right now, is because we are in the multiplying scalars and vectors section. All right. And so notice what we did there. We took the V vector here and we multiplied it by 3 in order to achieve a vector that's 3 times larger. Well, why did we need that? Because we somehow needed to get from B to D, but we were only allowed to use V and U as our sort of conduits of motion, okay? And that was just sort of like these are weird questions or funny questions. It's like the textbook is trying to stretch you into asking some questions to get you to think about in these ways. Okay. Oh, I just turned the mic off. Hopefully it's back on. Testing, testing. I don't know, actually. One last thing is the distributive property. Okay. Which basically means that I can take a scalar and it's the same as Ku plus Kv. All right. Which basically, if I have like U and then I add V to it, all right, that's U plus V, which is this. That's from yesterday. And if I multiply it by 2, then this guy here is 2U plus V. But another way of looking at this is if I do U times another U, or plus another U, plus a V and plus another V, I've basically done the same thing. And what are these purple lines here? This is 2U plus 2V. So basically what that means, it's 2U plus 2V. And basically what I've done is I've either added U and V first, which is basically this. I've added U plus V first, and then took the result and multiplied it by 2 to get that. Or I took twice U and then added to it twice V, and I ended up getting that, which is the same thing. And so basically that's why it's called basically what it means that the distributive property is valid for vector addition, meaning I can do this or I can do this, and in both cases they will get the same results. Okay, that's just something to keep in mind. There's also something called the associative property, and that basically looks like this. K, let's say I've got a M vector and I need another. Oh no, sorry. Let me do it like this. KMU is the same as K U times M. No, sorry. It is actually the same, but I think the way the textbook uses it is it's Km times U, meaning I can multiply U with M and then multiply the result by K, or I can multiply K by M and then multiply its result into U, and I'll get the same thing under both cases. And that's pretty self-explanatory. Let's say I've got a vector U, and I've got a K value of 2 and an M value of 3. So here, I'll basically start with vector U, and then here I'm going to do 2 times, sorry. I'm going to do 2 times 3U. Okay. So what that means is I basically take 3U first. This is 3U. And then I multiply it by 2, which is that. Okay. Or I could do 2 times 3u, which is actually just 6u. And basically, that just means it's 6 U's, 1, 2, 3, 4, 5, 6 U's. And if you notice, that's actually the same thing, right? So this is 6U, and this is 2 times 3U. Basically, that just means you can multiply scalars with each other and then into a vector, or you can multiply one scalar into a vector and take the resulting vector and multiply a scalar into that, which is called the associative property. All right, and that holds for multiplication as well, just like the the distributive property does as well, things like that. So these are just properties for vectors that you want to keep in mind as you kind of run across and you start doing some algebra. These vectors basically behave just like regular, everyday scalars algebraically, more or less. There's one thing that you can't do, and that's something like k plus u. No. That's like taking oranges and plus elephants and saying you've got, let's say I've got 3 oranges and plus 6 elephants, and saying that you've got 9 what? You got 9 what? What? You don't have 9. You got 9 things, right? But you don't have like 9 orifices or whatever. Basically, what I'm trying to say here is you can't add a vector with a scalar because it just doesn't work. All right. Anyway, those are some things that you're going to want to keep in mind for multiplying vectors and scalars. It's section 6.3.